Hello everyone, in this section we're going to discuss the open loop tuning for PID controller. Just to recall, in the previous section we have discussed the closed loop tuning for PID controller. The Ziegler and Nichols methods, they have two tuning methods for PID controller. One is what we call it closed loop tuning, or we call sometimes the ultimate cycling method. The second method is we call it the open loop tuning, or sometimes they call it process curve or process reaction curve, and we're going to see why we call it process reaction curve. The main difference between the two tests or between the two methods is, as from its name, is open loop tuning. So this is the feedback control loop. In the open loop we have the output from the controller. So this is the controller. The output of the controller is in manual mode. So the input to the final control element, this is the final control element, is entered manually, and normally we use the step input to the final control element or for the control valve. So the step one to do the open loop test is to find the process or the purpose of the open loop test is to find the process dynamic parameters. We have three main parameters that we should find them using the curve or the process reaction curve. One is the process gain or Kp, the time constant tau, and the dead time. These the parameters are the most important parameters, or they call it process dynamic parameters. In this case, as an operator, the output should be monitored by the operator all the time. So here we should, always look, to the output of the process and maintain them within a reasonable time, because here the response or the input signal to the final control element is manually. Step 2 here is explaining the process reaction curve, which we apply as a step change. So here it's the manual, so we will apply the step change or a unit step to the valve. This is the valve here. So this is the final control element from the so this is a manually control output signal will be entered to the final control elements. So we're supposed to get or obtain what we call process reaction curve. So after applying the step signal or step input to the final control element, so here we have the step input or step response, step signal, and we have the output or the process performance here. So this is what we call it process reaction curve. This is very important. So here is the input and here is the output, which is a process reaction curve, and from its name, process reaction curve, this is what we are looking for. So we can determine the process parameter, which is the process gain. Okay, so this is Kp, the dead time Td, and the time constant. As you can observe, at this time the step change has or the input signal has changed, while the output, we can see here it didn't change immediately after the input time, or after we have changed the input signal. After that, starting to perform or change. Just to mention that, please pay attention to the process here. So the process variable, or the process performance, and this state has reached what we call it the state or the steady state value. So here is going to continuously perform in the same we can say level. This kind of response, we call it first order lag plus dead time. So from the model or reaction curve or process reaction curve, we have to find first the process gain Kp, dead time Td, and time constant. These three parameters are the most important parameters that we can get it from the graph of the process dynamic or process reaction curve. The explanation for these parameters, we're going to explain it in details. For the process gain value, it shows actually how the control variable changed with respect to the change in the controller. In other words, we can say it's the ratio of the control variable to the the change of the control variable to the change of the controller output. So we can see it's the delta of the process variable over the delta of the controller output. And regarding the time constant, it indicates how fast the control variable changes. So the time constant is indicating how fast the control variable change with respect to the input change. The dead time indicates the time it takes for the output to start changing after the disturbance or after the step change. So after we change the input, we inject the step signal to the final control element, then we can see how much time it will take the process to change. So this time, from the time that you change, as we can see, from the time that you change the input until the time, for example, it is almost here, so this time will be what you call dead time. And the process parameters can be determined as shown in this slide number 5. So as we discussed, the process gain, or Kp, is equal to the change in Bphi over the change in the controller output. So this is very important to know. And then the step number 2, in this step, or we draw a straight line tangent to the curve at the point of inflection. The maximum slope indicates the point of inflection. So in this case, we can see this is the point here where the steepest point can be figured out. And we're going to explain it in the next slide clearly. So here, the point between the occurrence of the input change or the output of the controller, this point now, as we have discussed, this is the input and this is the output. But the input is what? Is the output of the controller, where it goes to the final control element. So here, this point explaining or illustrating the starting of the input change. So the dead time is the time line, or the time between the starting of the input change until the input of, or the point where the intersection happens between the line, the tangent line, and the time axis here. So this point and this point. So the time, or the dead time, again is the time, the duration from the output of the controller or the input change and the point of the intersection of the tangent, this tangent with the time axis. So this is what we call it, dead time, and we're going to explain it in the next slide also. So this is the dead time, is the distance in time, it's in time between the occurrence of the input change and the point of the intersection of the tangent with the time axis. To find the time constant, tau, we draw a horizontal line at 63.2%. So this is the output from here to here, okay, the output, or the process dynamic, or the process reaction, or we can say also process variable. So we have to calculate the 63.2%. So this is very important. You have to know the 63.2% of this line. For example, here, sorry, it's not this one. So you have to know the 63.2 of this distance, or this difference, and then you have to make a horizontal line and intersect it or connect it to the process variable. So the time difference between the end of the dead time and the 63.2 of the total process variable is, we call it time constant, which is 63.2% of the process variable. And this is very important. It will help you to measure how fast the process is changing with the change in the output of the controller. So here we go. It's again the figure it will explain and illustrate how to calculate the dead time constant from the process reaction curve. So again, this is very important. That's why I'm repeating this. This is the input signal, okay? It's a step input. They call it step input, okay? And this is the output here. So these two signals are very important, okay? So we have to find the time, the dead time, and the time constant. Again, I will explain it first, how to find the dead time, and second, the time constant. These figures and these calculations are very, very, very important. First of all, you have to draw the maximum slope, or the maximum tangent line, which touches the time constant here, or the time axis. So also we in the output here, in the output signal, we have the time axis. in both figures. So here you draw the tangent line, and the dead time is the difference between the starting of the output, or the time where the output of the controller or the input signal starts to change, until the end of, until where is the tangent line touch the time axis. So here, this point here is touching the time axis. So from this point to this point, we measure the time, and we call it the dead time. So this one will explain to you how much delay between the input signal and the output performance, or the reaction output. Second is to find the time constant. The time constant, it will start from the end of the dead time. So this is the dead time, it will start from here. And then you have to calculate the 63.2% of your measurement, your process variable. So you have to know how much the process variable here, and you find the 63.2, and then you draw a horizontal line from the 63.2 until it touch or intersect with the process reaction curve, and then you bring it down, and you will find the time constant. So the difference between these 2 points explains or indicates the time constant. So after getting these process parameters, including the process gain, dead time, and time constant, we use the Ziegler-Nichols tuning formula table. This table is for the open loop tuning, so it's different from the closed loop one. So for example, if you would like to have only proportional controller, so you apply, in order to find the gain, so this is the controller gain, you will have to divide the time constant by the process gain multiplied by the dead time. If you would like to apply or consider the proportion and integral controller, so you use this equation, and you can see that in this case the gain is a little bit reduced, in order to reduce the oscillation of the process performance. And then we have to calculate the dead time here, or the integral time, sorry. For the PID, we use this table. So in order to apply the PID, so you have to find the gain by using this equation. For the integral mode, you have to find or multiply it by 2. 2 multiply the dead time, it will give you the integral time. While the derivative time, you can get it by multiplying the 0.5 by the dead time. You can notice here in the PID, we have the gain here. We can see in the proportional, it's this equation, and when we are using the PI, we reduce the gain by multiplying by 0.9. This will reduce the gain in order to reduce the oscillation. But when we are using the derivative, there is amount of it's dynamic, and it will not having a lag, so we can increase the gain in order to speed up the process. Another term here which we have to consider also in order to measure the controllability of the process loop. The controllability of the process control loop decreases when the ratio of the dead time, so we have the dt to its time constant. So TD over time constant This is what we have to calculate in order to measure the controllability. As the TD over tau, which is time constant, increase, the controllability of the process will be decreased. So this is, you should consider. And this table will help us to measure the controllability. So we have, for example, if we have the dead time over time constant equals to 0.01, then by calculating the gain or the controllability, we have for the proportional, we have to find tau over process gain multiplied by dead time. So in this case, TD over the time constant is 0.01, so 1 over 0.01 will give us 100 over kb. So this will help us to find the Kc. For the BI, we'll use this equation, 0.9 tau over Kp over Td multiplied by Td, and also the PID. And this is the same Ziegler-Nichols controller tuning table for the open loop. So just instead of applying finding the Kc and Ti and Td, we'll use it. We'll consider only finding the Kc, and by finding the Kc, we can see how is the controllability of the process loop. So in this example, 0.01, we can see that the Kc in this case will be high, because the high number here. This is comparing to the second case, where is the Td over tau equal to 0.1. So we can see here is higher gain. That's mean, or higher ratio it's higher gain. So the controllability, so it has a higher controllability. So here again, for the condition 2 or example 2, when the ratio of dead time over the tau equal to 0.1, we can see the process gain has lower control value. For the third case, here is equal to 1, the ratio is 1, so we can notice that the control gain is getting lower. Between, or which one of these conditions or examples has more controllability or higher controllability? So this one, or this ratio, when Td over tau equal to 0.01, it is the highest, it has the highest controllability value. Again, when the ratio is decreased, the controllability is increased, and the vice versa. So in this example, compare the following processes to the controllability and the speed of the response. So here we have the Kb, process gain, process 1. So we have 3 processes. This is process 1 and this 2, and here is the third one. We have the process gain, we have the dead time for each one, and the time constant. So first we will start to find the controllability. In order to find the controllability, you have to find the ratio of Td over tau. So the dead time over the time constant, it will indicate to us the controllability of the process. So dead time over the time constant for the process 1 equal to 0.47. So the process, this is for process number 1. For the process number 2, we have it 0.5, while the process 3 equals to 0.2. So which one is higher. As we said, higher ratio of the dead time over time constant indicates or represent a low controllability. So the lowest one here is the process number 3. It has 0.1. So here we have the highest controllability. So process 1 is higher compared to which process? Process 2. So process 2 is 0.5 while process 1 0.47. So the process 1 has more controllability or higher controllability than process number 2, but lower compared to process 3. So this is important. If I'm going to ask you in the exam to compare between 3 or 4 processes, so you have to indicate for each process you have to compare that process to the other processes. So 0.5 is the lowest because it has the highest ratio, and as we said, the process 3 has the highest. Another point is the speed of the response. This is also very important. As we have said, the dead time, we have to compare the dead time. The dead time indicates how much the delay between the input signal to the final control element and the output of the process. So it will indicate how it will start fastest, or which one it will start faster than the other process. So here we have 1.4 minutes for process 1. Process 2 has 5 seconds only. Process 3 has 2 minutes. So we can see that process 2, it will start immediately or faster than the other 2 processes, while the process 1, it will start after 1.4 minutes. So this is it will start faster than the process 3, and it will be the start fastest compared to the. So we have a mistake here. So this is 5 seconds. So this one will be the fastest. Okay, and then it will come process number 1, and the last one will be process number 3. So these you have to consider in this one, in this example. For the tau, which is the time constant, it will indicate how fast is the process. In order to reach the steady state value or the steady state final value. So here we have the 3 minutes for process 1, 10 seconds for process number 2, and 10 minutes for the process number 3. So process number 2, it will reach the steady state fastest. So number 1, the process number 2 will be reaching the steady state's value faster than the process 3 and process 1. The second process, which will reach the steady state value, will be process number 1. Okay, and the third one will be process number 3. So it will take 10 minutes in order to reach the steady state value. So this example is very important, but you have to consider the mistakes here in the the notes. So please pay attention to these mistakes.